All right, hello and welcome everyone to our webinar on multivariate forecasting. Thank you for joining us today. This webinar is part of Forecast Pro's educational series, and we typically run these once a quarter, but in particular, the webinar we're doing today, which you can see as multivariate forecasting and methods, is going to be a companion webinar to our most recent installment of the Succeeding with Forecast Pro webinar series. That one's a little more focused on the product usage, and that was hosted about a month ago by my colleague James Barry. And if you'd like to check that webinar out, I'm putting a link in the Zoom chat right now. We will be taking Q&A at the end today. So if you think of questions, please feel free to put them in the chat whenever you'd like, and we will take a look at the end. A little about myself. My name is Franklin Ray, and I'm a trainer and consultant with Forecast Pro. So that means I routinely assist clients in getting set up on the Forecast Pro software. I help them with solving challenges related to data and integration and the use of the tool. And additionally, I'm a speaker on the Forecast Pro series of educational events, so some conferences and workshops that some of you may have attended in the past. And my background is in data analysis, math, and marketing analytics, kind of broadly speaking. So what are we covering today? Today's webinar will last about 1 hour, and as we said, it is on multivariate forecasting and methods. This is a term that has many meanings, but specifically today, we're going to zoom in on a type of multivariate modeling called dynamic regression. So we're going to review what regression is, both in the classical setting and what we mean when we use the word dynamic to go along with that. We'll see how it's used in Forecast Pro with two examples. One is going to be on electric power demand, and the other will have to do with using planned housing starts to predict demand for ceiling tile. And finally, we'll wrap up with extensions and conclusions and a Q&A session. So once again, I encourage you, if you have questions that come up in your mind during the session, either write them down or put them in the chat, and we'll get to them at the end. So the first thing we want to do is understand what is meant by regression. And at its core, regression is a method of fitting a relationship between a variable that we want to better understand with one or more variables that can help us predict it. If you're comparing the variable that you are trying to forecast or analyze with one variable, that's called single regression. And if you're using multiple inputs, that would be called multiple regression. The variable that we're trying to understand is variously referred to as the dependent or endogenous variable, whereas your predictors have multiple names. Sometimes we call them independent variables or exogenous variables or regressors or sometimes just predictors. And the picture I have up on the screen right now is a kind of classic example of what we call linear regression, and it may even be something that is drawn from an example that you've already seen in a stats class. This is showing us a proposed relationship between hours studied and the score on a test of maybe one student, maybe a class full of students. And the assumption is that these are linearly related somehow. So an additional hours studied is going to increase the score by some amount. If we can establish a relationship like that, in this case between hours studied and the test score, or in the real world between some economic factor and the demand for a good, we can be more confident in our prediction of how the variable we want to understand changes in time. So this is what we call linear regression. If we're trying to forecast something, the idea here is that we can use the independent variable as a predictor of the dependent variable. And you can see here now, if I have new data points, say a couple of new students take the test, we can predict based on that relationship where their scores are going to lie. And that's what we see with these with these new data points here. Now, the other piece of this is if you're a forecaster and you're forecasting some item, you're already familiar with time series modeling. And this is something we do in Forecast Pro. Here in the next picture, I have a time series showing, and this is the history of, say, a bunch of test scores. And it's not entirely unreasonable, for instance, to think about forecasting the student's next grade on the test using a time series methodology. And this would mean that you're just thinking of past scores to predict future scores. If you have a smart student who's getting A's and A minuses, it's not unreasonable to use the past behavior to infer that their next grade is going to be an A or an A minus. So these are two two related methodologies that we can use for forecasting. But today we're going to explore the idea of regression and talk about some of the advantages and disadvantages. All right, so advantages of regression. As we said, this allows us to introduce explanatory variables. These bring real-world data into our model, and these could be variables like pricing, advertising coverage, weather, economic factors. And these models are uniquely powerful in that they allow us to quantify what the relationship is between the input or regressor variables and the output. So not only will we have one driving the other, but we'll establish exactly how much the change in the dependent variable is impacted by the change in the independent variable. One major upshot of this is that we're able to create what-if scenarios, meaning that if I know the impact of a price shift has in my demand, I have that relationship established statistically, I'm able to then model scenarios like what would happen if the price went up by $5 or $10 or is doubled, even if such a situation hasn't happened in real life, because we know prototypically what a change in the one variable does to another variable. Moreover, we can take advantage of the fact that oftentimes changes into the demand for our items lag behind changes in the independent variables. For instance, a policy or price change might not be felt in the markets until weeks or months later. But if we know that a relationship exists, we can get ahead of the expected changes and thereby improve our forecast's accuracy. And to be perfectly fair, we want to cover some of the other side of the coin too. So regression models have some cons. They're not automatic. It's going to take additional expertise and judgment to set these up and validate them. And when you're building a regression model, you need a lot of confidence in these predictor variables that you select. First of all, you need to know what to go out and select for. Secondly, when you build these data sets, oftentimes you will need to forecast your predictor variables out into the future as well. And if these variables are hard to collect and hard to validate, the relationship between the independent variable and the dependent variable ends up being more tenuous. And lastly, models of this sort just take more work. So you're going to have to collect, clean, curate, and be confident in this data that you're going to use. So it's worth considering if a time series approach is sufficient, if it'll get you, say, 90% of the way there without the extra effort. However, in my experience, what we find is that there are industries and types of forecasts and types of items where regression modeling is absolutely beneficial compared to just using a time series approach, that is, just using the historic demand on the item. All right, we're going to get into a little of the nuts and bolts of how classical regression works. So again, as I said, at its core, regression is about expressing the dependent variable as a linear function of its predictors. And the other piece of the puzzle is that there's going to be some error term or offset. So I promise there are not too many equations over the course of this webinar, but this one's important. Many of you may recognize the first piece of this equation, y equals bx plus c, as the slope-intercept form of a line. And if you're wondering why we have the subscript t on both the input variable and the dependent variable, that's because we're assuming that these move through time as well. So we have an observation from this month and last month and the month before and the month before. Now we have this linear equation, but we know that our real world data is not going to conform to the line exactly. It's going to be offset by some error or residual. So that's where the E sub t term comes in. And as you can see in the picture, it's exactly that. We have the hours studied and we have the test score, and we've established a linear relationship between them. But in actuality, the scores of the students are not perfectly on that line. They are offset by some amount. We end up knowing that we have a good estimated relationship between the independent and dependent variables if we can choose a linear equation that is going to make those offsets or error terms as small as possible. And I can show you how that works. What we do to fit the regression line to the data is something called the ordinary least squares method. Now we have a slightly different picture on here, but mathematically what this amounts to is choosing the line for which the offsets or errors have the minimized squared height with the line. So we take each of our data points, like you can see on the picture, and we figure out how high it is above or below the line, and we take all those distances and square them and sum them up, and that gives us some statistic. And our goal is to choose a line with a slope and an intercept that minimizes the squares of those distances. Now, when I first learned this in a class way back when, I was a little bit confused with the squaring part of it. I was thinking, after all, squaring kind of blows up the big numbers and it compresses the small numbers, and why not use just something simple like minimizing just the height, just the absolute value above and below the line. And I want to get into this because I had a good teacher explain it to me, and I think it's worthwhile just getting it out there how this works. It turns out that if you don't square the results, the linear fit that you get is not guaranteed to be unique. Whereas if you do square them, you are guaranteed to get a unique fit to your data. So I have two pictures here from a very specific data set. And in this case, there are two candidate best fit lines. Actually, there are a lot more than that. But here are two possible best fit lines. And if you're just measuring the height of the data points relative to those lines without squaring anything, either line could end up being the same. So the blue heights are equal to the red heights for those candidate lines. And in that case, we wouldn't know which relationship between the independent variable and the dependent variable fits our data best. And in fact, in this case, you wouldn't even know if those data are positively or negatively correlated. So this is why we use the ordinary least squares method instead of something else. Now, we're not going to worry too much. If you have a software package like Forecast Pro, all that math is going to be done for you, but I do think it's worthwhile to know what is going on under the hood. Getting a little more into the practical part of this, it's worth talking about how to choose these independent variables. So broadly, what you want to do is think about how these fall into one or two camps. Some are going to be internal to your business, like price, promotional spending, advertising, even marketing analytics like likes and shares, audience that you can reach, that you can measure internally, versus variables that are selected from external sources to your business. And these would be things like the weather, economic data, competitive behavior, or the demographic landscape, or municipal information. And often case, it's these externally sourced variables that are very tantalizing because we always assume there's some relationship that is explaining all the demand for our items and what is going to happen in the future. And if we could just capture that and establish it, then we'd have a really, really accurate forecast. But the caveat is that these external variables for which you have less direct access are often the ones that are much harder to collect and validate and curate for your models. So there is some balance between using some of each if you're going to go down this road. And before we get into our examples, the last piece of this I want to talk about is what makes regression dynamic. So if you've been in Forecast Pro software, or if you're just learning about this for the first time, in forecasting, everything is tied to a time series, which means the demand for the items don't just happen all at once, they happen across time. Um, the dynamics refers to that time component. And this can take a few forms in practicality. One of these is lags in the dependent variable. So this is like treating a dependent variable shifted back some number of periods as its own independent or regressor against itself. So you think, how did demand last period or a seasonal cycle ago or two seasonal cycles ago impact demand today? And the other way we investigate dynamics are through the use of what are called Cochrane-Orchid terms. And that's a funny name for a methodology for extrapolating patterns in the lagged errors that the model introduces. This is under the theory that if the errors follow a consistent pattern, then there's some variable we're not explaining. And again, both of these are going to be calculated automatically by the majority of software systems, including Forecast Pro. All right, with all that out of the way, we're going to get into our first example. And this example has to do with electric power demand. The data we're showing on the screen here is historic data for sales per customer, residential sales that is, of kilowatt hours of electric power. And just looking at this, I've turned the forecasts off. We're just looking at the history. We can easily see that this is a seasonal data set and it spikes during the warm months, peaking in August. And then there is a secondary seasonality, a secondary sequence of spikes, and these occur in the cold months like January and February. And it's probably immediately obvious what's happening here. During the hot months, people are running their AC units. I know from my experience, AC tends to pump up my electric bill. My usage a little more than when I'm merely heating my house, so the spikes in the warmer months are higher. And the first thing we're going to do here is turn the forecast on. And as I said, it is probably worth just for the sake of baselining things, understanding what a time series forecast would do to this data. So if we want to check, I can go over here in the Forecast Pro software to the forecast report and open that up and arrange these together. And we'll go down here and we'll see that the model used to forecast this right now is exponential smoothing, additive Winters exponential smoothing. And that is, that's a time series methodology. This is not regression yet. And if we go into the within sample statistics, we can see it's actually doing a pretty good job. Our adjusted R squared, which is a measurement of how much of the history we explained, is 89.89 or 89%. And our MAPE, or mean absolute percent error, is 5.90. Now, what this is doing is it's comparing the fitted values of the model, basically what the model would have estimated to happen at some point in the past, as you can see that I just put on the graph right now, with the actual data. And of course, the model is not going to be able to approximate the data perfectly in all cases, but we're finding out how much it missed in different periods, what these gaps are in percentage terms, and averaging out the absolute size of these percentage gaps. And that's exactly what gives us this MAPE statistic. So as a forecaster, two things happen for me when I see this data. First of all, I look at the forecast and I say it's not an unreasonable forecast. I see the seasonality. I see the big spikes, the little spikes. Well, what we're estimating is that next summer, we're going to spike up, and in fact, the summer after that. And next winter, we're going to have a smaller spike. My forecast looks good. And the other thing I see is that my error is relatively low, whatever that means. My explainability is relatively high. I mean, 89% explainability sounds pretty good to me. Um, Under 10% error, not unreasonable. Um, but this is electric power demand we're talking about. And if you think about that industry, they really have a lot of control over that supply chain, right? From the point where the electricity is generated all the way to the substation, power lines, all the way to the box on the side of my house. Um, this is not like a shipping and receiving problem. This is not like if the truck gets to the location, we'll ship, and if it doesn't, we don't. And if we have excess, we put it into a warehouse. Electric power demand does not tolerate these sorts of errors. So we'll actually show that through leveraging independent external variables and creating a regression model, we're going to improve these numbers a lot and explain the relationships along the way. And if you just look at this and want to see where things are going wrong with the time series method, the weather's not the same every year, right? There were some moderately hot summers, but also we had a period where things were getting hotter and hotter and hotter, or at least that's what I infer from the power consumption for AC units. And the model's not immediately reacting to that. It is growing slightly, but the actual demand is overshooting what the model should have thought should have happened. And um, we get to a point where the model has kind of caught up with what happened, and then immediately the summers were not as hot. And now the model is overshooting. So there was error introduced when we were doing this method. All right, the next thing we're going to do is explore the regression variables that we brought in. So these are stored under here in the helpers section. And when you insert those into Forecast Pro, if you're a Forecast Pro user, they also come in through the data manager and they come in through the section called explanatory variables. You can bring those in on a CSV or an Excel sheet is probably the easiest way. And we have 5 of these. Um, Now, the helper variables or the regressor variables don't forecast themselves automatically. It turns out when we build the model, we can kind of tell them to if need be. But we'll just go through what these are. The first one is AC saturation. This is the percentage of the population in this area that even owned an AC unit over time. So you can see over time, looks like more and more people ended up buying AC units. Cooling 66 and cooling 76 are variables that are sort of normalized scores of how many days per month the temperature was over 66 degrees and likewise over 76 degrees, respectively, along with a factor that says exactly how much above those thresholds was it. So we get higher spikes when the temperature was much, much higher above, say, 76. Disposable income is just that. It's the income of the people in this area on average through time. And heating 55 is sort of dual to cooling 66 and 76 in that it shows how many days of the year the temperature dipped below 55 degrees, which would logically imply that people would be using up more electric power demand to heat their houses. And I'll show you something really cool in Forecast Pro that some people don't know about, which is that you can actually plot all of these on the graph at once. And what we can do is go to the graph, right click, go to settings, go all the way over here to items. And if I start multi-selecting these with my control key, and I'm just going to do the temperature ones because they had the spikes up and down, we'll enter this multi-item mode. And when I go ahead and apply that, we will see our sales per customer, aka the item we're trying to forecast, in yellow, but we also see the cooling and heating days plotted on the graph as well. And again, just visualizing this, you can see some very natural relationships cropping up. During the warm periods, we see the cooling 66 and cooling 76 variables lining up with the hottest periods of the year. And likewise, during the sub spikes during the cold months, we see the heating 55 variable being highlighted, even with the same shape and in the same place. So just by visualizing this, we can start to infer that these relationships really do exist, and understanding these independent variables that I sourced from real world weather data do have an influence on my demand, and I can use them to build a better model. All right, to exit the multi-item graph, we just right click here and say exit. And now we're going to talk about how to build a regression model. What you would do to set this up, we're going to be very hands-on, is go to the forecasting tab and select here dynamic regression. Now it brings up this box where I get to make some choices, like which of the variables get added to the model. There are also some other things in here that are worth talking about. One of them is this checkbox that I don't have turned on called automatically extend. The idea here is that sometimes you will source these variables outside from the real world, but the trajectory that you're trying to forecast for your item goes way out into the future, and you might not have sufficient data in your sourced independent variables to cover the entire term you're trying to forecast. So if you can't project your independent or explanatory variables out into the future on your own, you can have Forecast Pro forecast them. How does it forecast them? Using the Forecast Pro methodologies. So sometimes we have to do this because we need our explanatory or independent variables to cover the full time frame that we're trying to forecast. We're not going to do that today because the data I brought in did have enough length and stability to it to go ahead. The other thing that's available is this automatic dynamics. And this is checked right now, and we're going to leave it checked. But if I turn it off, you will see some other things become available in the system variables. And these are things like these lags and lagged error terms. If I wanted to control those myself, I could. It is generally a best practice to let the system figure out if there are relationships between lags in your demand with itself or patterns in the errors, and let the system do that on its own. The other thing that's in here are what we call indicator functions, and you can see these are denoted by like spike and step. And what these refer to is the ability of baking into your regression model the fact that something happened in just one period, like a relationship occurred in just one place and nowhere else. And this would be like a spike. You can imagine a string of zeros and then a spike up to one and then a string of zeros. So we just target one point in the data that we want to isolate. And the step one is similar, except this has to do with a before-after type of analysis, like if a variable kicked in at some point but did not exist before. So you can imagine here like a string of zeros, and then we step up to one, and then we're ones thereafter, like a stair step. These are also functions that we can use to replicate things like single-time price changes or special events or promotions in a regression model. We are going to let the system figure all that stuff out by itself. So I'm going to turn automatic dynamics back on. For building the model with the variables that I sourced and brought in as data, we generally have sort of two approaches. I like to think of them as starting with everything versus starting with one thing at a time. So starting with every possible variable under the sun and figuring out which ones work the best and tossing the ones that didn't, versus starting with maybe just one variable like AC saturation and then dripping in the other variables one at a time. Both are feasible. I like starting with everything, and that's the example I'm going to do, and we'll talk briefly about the other example. Selecting all of these, I can just add them to the model, and now that they're all part of the model, we can click OK. And if you'd like, you can look at the red forecast here and see how much it changes when I apply this regression model. Well, it changed a little bit. Visually, yes, but the overall pattern, maybe not so much. So we wonder, what is the upshot here? How much are we improving the forecast of electric power demand using all these regressors? Well, for that, we can go back to the forecast report and bring this up. And I'll arrange this to the top again. And we'll go in here, and we see now in the model details, I have a user-defined regression model. That's what we just did. And we have this printout of the variables that exist in this model. You can see I put in all five: AC saturation, cooling 66 and 76, disposable income, heating 55. And because we had turned automatic dynamics on, we get constants and lags in the errors over various cycles. And that's something that the software figured out on its own. We'll talk about what these statistics mean in a moment, but the first thing I want to show you is that in the within sample testing, we made some improvements. The adjusted R squared, the explainability of the history given the model has gone from 89% up to 99%. That is a big improvement. If we turn on the fitted values, we're going to see that play out. We're going to see a better shrink wrapping of the history with the fitted values, which indicates to us that we're explaining more of this model. The other thing is that the MAPE, or mean absolute percent error, has gone down from 5 point something to 2.41. So we've made an improvement there as well. So already by incorporating these variables, which when we looked on the multi-row version of the graph, we could visually see were related with my data, we have made some natural improvements. Now, can we get it even better? It turns out probably. Up here in the regression test statistics, we can see some of the variables I brought in are marked in red, and it says marked regressors are insignificant. Well, what insignificant means in Forecast Pro is that the confidence that this has some meaningful impact on the model is less than 95%, or the 95th percentile. And that's what's shown right here. Now, you might look at these and you might think if disposable income is related to my data in up to the 87th percentile, or AC saturation up to the 93rd percentile, that this is, meaningful to you and you want to leave them in, and this is the model you want to make. That's absolutely fine. That's a choice. But ideally, we want all of our variables to be as significant as possible. The other thing we want to check for are these coefficients. And the coefficients tell us the strength of the linear relationship between the independent variable and the model we're trying to predict, aka the power demand. We always want to check whether these coefficients are directionally accurate, if they make sense. A positive coefficient means that there is a positive relationship between, say, AC saturation and electric power demand. This is telling us that that coefficient is positive and it's relatively high, meaning for one more percentage point of AC ownership in this area, we expect electric power demand to go up by 553 kilowatt hours. Now, when I look at the disposable income one, not only is its significance percentile the lowest, but also the coefficient is negative. Now, it's a tiny number, 0.0 something, but negative is weird to me because this is saying if I have another dollar in my pocket, my usage of electricity actually goes down by something like 1 cent. What does that mean logically? I guess if I have more money, I don't just like feel comfortable running my AC longer. Maybe that's not really how it works. Maybe when I have more money, I get out of my house and go on vacation. Um, so income here is negatively correlated with what we're trying to predict, and that doesn't really pass the smell test. So what I'm going to do is start with this one and remove it from my model. We're going to remove disposable income by right-clicking and saying remove disposable income from the model. And when I do that, everything will recalculate. So all these coefficients, all these percentiles will recalculate. We see here, just by doing that, actually one of the autodynamic terms cleaned up. There was a red one here before that was insignificant. Now it is no longer insignificant. But also something has changed with the AC saturation. For one, the significance of AC ownership to the model has gone down to only the 71st percentile, which is maybe not that great. But also the coefficient or the relationship has gotten weaker. So maybe what we can infer from that is there was some crosstalk, some multi-collinearity between disposable income and AC saturation that was going on behind the scenes. And this is the type of thing you want to think of as well. Do your external or independent variables talk to each other? In this case, what I can sort of infer is maybe when I get that extra dollar in my pocket, I spend it on an AC unit or a better AC unit. rather than just running that thing longer. So now we have a pretty good clue that AC saturation is maybe not the most significant to this model, and I'll go ahead and remove it as well. And after doing that, now we see that all of my variables are significant to the model, most of them above the, or all of them above the 99th percentile. Um, and when I go down to the test statistics, we see even further improvement. Well, it's a little bit, right? But every bit of model improvement I can get is worth it to me. So our R squared is still at 99%, and our MAPE has come down a little bit from 2.5 something to now 2.3. So we've improved the model kind of as well as we possibly could get it. Um, and I'm now confident that this is the model I want to use to forecast this demand. Now, I could have gone the other way, right? If I could have started with just cooling 66 or just cooling 76 or just AC saturation. Um, and if I had done that, I would have come down here to what we call the variable specification test battery, where it shows me all the variables that I had not used in my model. And you can see some of these we actually had used, but I dropped them out. And it will suggest to me, if you included this in the model, would it be significant in any way? So what I could do, if we wanted to go the other way, if I had not started with everything, is introduce a new one of these, a new regression model, and just start with one. Maybe just start with cooling 66 only and bring that into the model and rerun things. And now where are we? Well, we have a significant model, only using cooling 66, no problems to speak of. The MAPE is a little higher. The explainability is 1 percentage point lower. So we know it's not as good as a model as the one that we started with everything and eliminated. So probably to improve this one, we need to add some things. But when we go down into the test battery, it will say, what are some other things you want to try related to this model or related to what's in your model to make improvements. And in this case, because we only started with one variable, it's saying, hey, would you like to try lagging that variable by one period and seeing if that's significant. But if I'd gone in here and added everything else like we did before, but merely unchecked them, it would test against my unchecked regressors and say, do you want to add those? And here we're going to line this up with the first example we did, where it says try adding your heating 55 and indeed your cooling 66 to the model. So we would add these one at a time. Um, and it would also tell me try adding cooling 76 to the model. And we would do that one by one. And now we're back at the exact model we had before where we used exactly those three. So we want to put things in the model in a way where we are either eliminating the ones that don't work or introducing the ones that do work. And this is basically the in and out of creating a regression model. We need, like I said before, a little more thought process to apply this because we really do, in a way that you don't often see with the time series modeling, need to come into the forecast report and analyze the relationships of the variables we introduced with the model itself and whether they mean something to us. Now, I have another example ready to look at, and this one has to do with these lagged variables that we saw hinted at before. So I'm going to switch to another project that I have ready to go. And this one also has a single item that we're trying to forecast. And this one is ceiling tile in square feet. And on here, we have a time series model. I believe it's Box Jenkins. And we got a very simple model. Even though the history kind of wiggles up and down and there's implication of some seasonality, I did not get a seasonal model out of time series. It's indicating to me that this data is kind of hard to explain. But what I want to do is build a regression model that takes advantage not just of an input variable, but of a lagged input variable. Now, I have two input variables ready to go. One is cost of goods. That's kind of logical, right? If my ceiling tile ends up costing more, then that cost gets passed on to consumers and their demand will go down. The other one I have, however, is housing starts. And you can see the housing starts almost look like my historic, but not quite. The variation is a little different in several places, but these are going to end up being highly, highly related. And the idea here is that housing starts is not just a good predictor of demand for ceiling tile. Obviously, that's true. If I build more houses, then we need, or structures, we need to put furnishings in them. Um, but it's going to end up being a lagged indicator, or rather, the demand for ceiling tile lags behind the housing starts. Now, housing starts are something that I got municipally. I went to the city and I said, "How many building permits did you approve this period or over this many years?" Um, that ends up being a leading predictor, which is to say my demand is a lagged output of those building permits, because when you get the building permit, it takes some number of months. In this case, I happen to know 8 months while the foundation is being poured, while the house is being framed, while it's being wrapped, while the electrical system is being installed. All that we get down the road to when we do inside furnishing, kind of the cosmetics, like the ceiling tile. And that's what we're going to see when we build the model. So I'm going to go with the same approach. I'm going to go to regression, and I'm going to start off bringing in cost of goods and housing starts. We'll bring them both in and hit OK. And I just want to point out before we do this, the error on my time series model was not so great. It was 52%. We'll see if we can improve that. So I brought in these two variables, and we made some improvements. MAPE has gone way down. But when I look at my test statistics, things are really out of whack. Um, there are some issues here, and that's because I haven't applied all of my expertise to the model. And what are the issues? First of all, we don't have significance for either of the variables, so it's telling me, hey, you might not want to use these, which I know I do want to use them, so we're going to have to make some improvements here. The other thing is cost has a positive coefficient, which I really don't like. This is kind of saying that when the ceiling tile costs more, people are going to buy 46 more units of it, and that is illogical. And the housing starts are going the opposite direction. More housing starts is leading to negative ceiling tile. So I don't like that either. But fortunately here, rather than just playing the game of removing stuff until it looks good, I have additional knowledge up my sleeve, which is what we talked about. And it is that these housing starts are a leading indicator of my demand, and it's an 8 month leading indicator. So what I'll go in here and do is say we need to lag this variable by 8 periods. And it will give me some automatic ones to choose from, like 1 period, 2 periods, one seasonal cycle, two seasonal cycles. But I want to customize this. I happen to know it's 8 in this case. And when I choose this, we're now not using just the housing starts to predict the ceiling tile. We're using the housing starts rolled back 8 periods to predict next period's demand for ceiling tile. And when I apply that, the model has kind of cleaned up itself to some degree. Now we get the expected negative relationship to cost of goods. So even that was improved, even though that wasn't the one we touched on its own. And we get the positive uh, indication through the ceiling tile. So we're adding some more square footage of ceiling tile demand for every additional housing start. And we have significance on both of them. Now, some of the auto dynamics are still a little messy. I could try to continue to improve by looking at that. Um, and moreover, just eyeballing the forecast, things look a little more reasonable than where we were before. And lastly, in doing the examples, I'd be remiss if I didn't mention the fact that dynamic regression is not the only model type in Forecast Pro that can ingest external variables. The other one that can is machine learning. Um, the thing with machine learning is that it will input anything you tell it to, and then behind the scenes, it will use the machine learning package XGBoosted trees to come up with a model. Um, the upside of using machine learning is it's been tested thoroughly in and out, and it's a very accurate methodology when it is compared to other possible methodologies, but maybe at the cost of lower explainability. So when I build a machine learning model that introduces independent variables, like I can do here with my cost of goods and my housing starts, we will not get the same sort of test battery that explains to me if the relationship is positive or negative, or if it's significant or not. Nonetheless, I can toss these in to the model by checking them, and I can hit OK. And we can see now we have a /ML machine learning model on my ceiling tile. We see again that's user defined. And what machine learning does in Forecast Pro is essentially look at features of all the data you put into the machine learning model. And that is incorporating not just your own history, but also any of these explanatory variables. And it's figuring out which ones are important in terms of moving the forecast up or down. And it does that by building some branching trees that decide at every feature introduction, do I need to move the forecast up? Do I need to move it down? And those trees have a certain depth. But like you're familiar with, out in all the other AI tools and machine learning tools that we see out there, um, it's really, really hard to say under the hood exactly how we got to this point. You're not going to look at this and say, for housing starts, well, gain, coverage, and frequency were this as opposed to some other numbers. So therefore, I know exactly what is going to happen uh, with my demand and why. We just sort of have to try this model, and if it generates accurate forecasts, then feel confident going forward with it. So machine learning is able to involve not just your history, but all the other input variables you have. Um, but although it's very good at doing this, it's at the cost of you don't get to explain what those relationships were. Now, when we introduced this, it's actually funny. The MAPE went up a little bit relative to the other models. If we looked at fitted, we would have some mismatches in some places. So maybe in this exact context, I would want to take this and say I'm more comfortable using my regression model instead, which had a little better fit. But we don't have fitted values for the whole series because, again, some of these variables are lagged, and we only get to explain part of it. In this case, the error was a little lower. So kind of two competing ways of using these. Dynamic regression, of course, being much more hands-on. You are going to be doing a lot more of the thinking and the analysis when building a dynamic regression model, but the same functionality is also possible with machine learning. All right, we're getting down to the end here, and I want to leave time for Q&A. So I'm going to switch back to our slides. Just to recap some of the things we talked about, model validation is a big part of building regression models. Your model must make economic sense when you put it together. You need to check things like, do the coefficients have the proper sign? Are they significant? Are the variables we selected significant to the model? And the other thing that is part of this when you're doing this work to build a regression model is to avoid overfitting the parameters if possible. So we don't want to take one data set and throw 10 or 20 explanatory variables at it and just try to identify every feature. First of all, I think personally in the long run that ends up being unfeasible to maintain all those input variables. But moreover, there's this idea of being parsimonious, doing the most with the least number of resources recruited. I guess working smart, not hard. So if you can explain your data to, 98% accuracy with two variables, and adding 5 more variables only gets you up to 99%, you probably want to stick with the two. So the thought process and the validation is, as we've seen, a pretty big part of building a regression model. And just to add some conclusions, why did we do this topic now? Well, I think it is always on people's minds. what can I do to kind of go above and beyond just leveraging the history of my items to build a forecast? Um, and also, it's not really, out of the ordinary that we see things in the news, just out in the real world. Economics, inflation has been in the news a lot. Cost of gas has been in the news a lot. I mean, you can use your imagination, or you can just, turn on your favorite news source and imagine all these things that are going on in the world that have real life economic impacts on demand for your goods, if you're a demand planner. So um, I think this is a topic that is worthwhile to explore, um, in order to introduce the idea of what can we do to bolster some of our models, but also going hand in hand with the idea that if you're going to go down this route of bringing in independent variables to improve your forecasting, there are some questions about the um, the additional effort and expertise it takes, alongside, um, does that effort lead to meaningful improvements above the time series approach? Sometimes it can make sense to test both. And if the time series is doing well enough, if it's getting you into an error band that is acceptable for you, maybe plus or minus 5% error is an acceptable error uh, band for your demand to live in. And you can live in that band without doing the additional work of curating all of the external variables. That's fine, but it ends up being worthwhile to start thinking about this stuff, just so you know that it is available. Like I said, this webinar goes hand in hand with our Succeeding with Forecast Pro webinar, which I put a link to in the chat at the beginning. I am going to pause now for Q&A because we are just about at the end of the time.